Yeah. All right. So welcome to part 2 and therefore case 2. Right. So we are proving the ELP theorem. And let's make a drawing again. So we have chosen a tight cut, a non-trivial tight cut. C partial of x. This is x, this is x bar. And we have the property, this tight cut has the property that there exists an edge E, UV, so that the graph induced by x minus u and the graph induced by x bar minus v are both connected. So this we already know. The first case was v is the only neighbor of u that lies in x bar and u is the only neighbor of v that lies in x. Now we are not in this case. So I'll just say case 2 is not case 1. Right? Therefore, one of the two vertices has more neighbors on the other side. So I may adjust notation so that u has at least one neighbor in x bar that is not equal to v. Adjust notation so that the neighborhood of u intersected with x bar has cardinality at least 2. So to show that, let me just put one edge going like this, going somewhere to some vertex that is not equal to v. Okay, so this is the situation we are in. And as I said, the general philosophy of this proof is to deal with a matchable graph that has that satisfies the hypotheses of lemma 5.5. In the earlier case, that matchable graph was very natural in some sense. It was g minus u minus v. In this case, it will be somewhat less natural, but it will work, as we shall find out. So, we won't delete any vertices. We will delete some edges. Okay? The edges we will delete are these edges. The edges incident at u whose other end is in x. Let us call this capital F. F is the set of edges that are incident at u in the graph G and not in the cut C minus C. Is that correct? All the edges incident at u that are not in the cut C. So the other end is again in x itself. Right? So just as an example, I will consider there are 3 edges going like this, and this is my set F. Yeah? Or there could be more edges, I don't know. But there is at least one edge, right? Because the graph induced by x is connected. So you will definitely have some neighbor in the set x minus u. So definitely cardinality of f is at least 1, if not more. Yeah? Okay. And we will consider the graph G prime this time to be G minus F. Notation is slightly different from Lucchesi-Murty. They call this the set R. I don't like R. R is for removable edges. I don't like this. And they use G double prime because it is case 2, and then everything is the double prime. So I'll just do single prime. Okay. So this is our graph G prime, G minus F. This is going to be our graph that is matchable. Let's check that it is matchable. Does everybody believe that this is matchable? Do you see that this is a matchable graph, G prime? Original graph was matching covered. I've deleted only some edges incident at U, not all edges. Yeah? So it is matchable, right? Yeah? Okay, so G prime is matchable. Now we need to identify an even cut in G prime that satisfies the hypothesis of lemma 5.5. Both the shores should induce connected subgraphs, and the edges of the cut should be unmatchable in G prime. Those are the two hypotheses we need. So think about that. Can you come up with a cut? Well, I want a specific answer. Maybe there are multiple things that work, but I'm not going to do that. You can try that in your free time. Right. So, can you come up with a cut in G prime? Oh, am I using the mic? I'm not using the mic. Okay, let me use the mic. All right. Okay, so see if you can come up with an even cut in G prime that satisfies the hypothesis of lemma 5.5. Thank you. Good. Yeah. So DIY, quick DIY. Locate an even cut in G prime that satisfies the hypotheses of lemma 5.5. Right, so both shores should induce connected subgraphs. That is one hypothesis. And the other one is that edges in the cut should not be matchable in the graph G prime. Right? Can you find such a cut? Somehow it should be related to C. Just like in the previous case also, it was somehow related to C. Right? We took, instead of partial of x, we took partial of x minus u in the graph G prime in that case. So similarly, here we have not deleted any vertices. We have just deleted a non-empty set of edges. So if you have a candidate, raise your hand and I'll come and talk to you. Okay. Anybody else? Okay, so looks like everybody has figured it out. Good. So we will consider partial of x minus u. So let's say we call this cut D. D is partial in the graph G prime of x minus u. Yeah. I'll also draw it. Maybe I'll just use yellow. Maybe I should use a different color. Orange. Okay. So the cut D is basically this. Its two shores are x minus u and x bar plus u. Yeah, this is the cut in G prime. Yeah, so it's basically everything is there, only these blue edges are missing. Yeah, do you all agree this is an even cut? That is clear. Do you agree that both the shores induce connected subgraphs? Yeah, here we are using the fact that the graph induced by x minus u in particular is connected. This one anyways we know it is connected because it is the shore of a tight cut, and we are including u which has a neighbor v. Therefore this whole thing is connected. Yeah, and these edges don't matter as far as the connectivity is concerned because they are actually in the cut, not in the shores. Yeah, so the shores are connected, and do you all agree that the edges of this cut are not matchable in G prime? Check that. Convince yourself that the edges of this cut are not matchable in G prime. Yeah? Yeah? Everybody convinced? If they are matchable, you will get a contradiction to the original cut being a tight cut, as in the previous case. So therefore, this cut does satisfy all of the hypotheses in the graph G prime. Yeah? Good. We will apply lemma 5.5 therefore to G prime comma D. Yeah? So by lemma 5.5, there exists a Dulmage-Mendelssohn barrier in G prime such that the barrier and all of the odd components live on one and the same shore of D. Yeah. By lemma 5.5, there exists a Dulmage-Mendelssohn barrier B prime in G prime such that B prime and vertex sets of all odd components lie on one and the same shore. Yeah, so everything will lie inside x minus u, or everything means all of this thing lies inside x bar plus u. So we could either consider cases based on that, but we will actually consider cases based on the location of the vertex u. Okay, and that will of course be exhaustive. So either the vertex u is in the Dulmage-Mendelssohn barrier, or it is in one of the odd components, or it is in neither of them, because there could also be even components. Yeah? These are all the three possibilities. The vertex u either is in B prime, or it is an odd component of G prime minus B prime, or it is in an even component of G prime minus B prime. The easiest case turns out to be, think about it. There are three cases. Okay, the DIY. See if you can figure out at least one of the three cases. Figure out at least one of the three cases, and there is no right answer. You all may figure out different cases. I would argue that two of the three cases are actually quite easy. The third case is the one that requires some amount of work. Okay, make a drawing and draw all the three cases.
three cases are with respect to you.
With respect to?
You.
With respect to you. Yes. Yeah. Yeah. Based on location of U. Right? So yeah, maybe I'll write it down. U belongs to B prime. U belongs to U is a vertex of odd component. These are the three cases. In two of them, we will actually conclude that the graph G is not bicritical, and we will be done by star. And in the last case, or one of these three cases, they are not necessarily in the right order. And in one of the three cases, we will actually conclude that the graph has a two separation cut, right? Some cases has to happen because bicritical graph exists. So, bicritical graphs are the problematic graphs. If you have figured out any case, raise your hand and I'll come and talk to you. What if it is trivial? It's still easy. So think about that. Okay. No, it's not clear, is it? But maybe you don't need to worry about that. If it is in the even component, think about the difference between G prime and G. Capital F. Can't they go to some odd components? Yes, some edges go from U to some odd component. Capital F edges. That we don't know, right? If U is an even component, we don't know where all this lies. Is it lying near X minus U or X bar plus U? That is not clear to us. You have to consider maybe Actually, that's an easier way. So if you use any component thing, so I'll give you a hint. When something creates a problem, make it disappear. I see. I did not think B prime is on this side. X minus U. And U plus. Yeah. That works. Right, that also we don't know.
If you use the vertex you will not be, then I will include you to the vertex value type. Then that is going to be non-trivial variable.
Good. No, but in this part variable, there's one concern. What if variable is trivial? But if it is not trivial, what's next? Doesn't matter. If you just include it in the variable, in the new variable, the original components are still K minus 1.
Some odd component. Then also if I include you to my dash, then I will have to put K minus 1 odd component.
What if it is singleton? What if the variable is single vertex? So what was the case? U is an
Odd component.
U is an odd component. Okay. Okay. So that you can do that case also. There's one case which is tricky. Inside that case, there is a tricky case.
Okay, and this
Yeah.
use
Think about it. At least two of the three cases are quite easy. Yes. Yes. Right. Okay. Okay. Which is what is trivial?
if P prime is trivial, if U is the only vertex, and this part is disconnected. Just suppose
P prime is trivial.
then
And it is only containing U. You mean P prime is equal to just the set containing U.
yes,
Okay.
then G prime induced by X bar, which is the same as G induced by X bar, is disconnected.
No, why? Why can't it just be connected with a single odd component?
Oh, okay.
If you delete one vertex, you just leave one odd component. So now what about the side? So if U is an even component,
and so the previous case and term will be a subcase of S. So that's the last one.
Why two odd components? What if there's only one odd component? So you're assuming that B prime is non-trivial.
B prime has to be non-trivial in G.
No, but B prime is the element isn't very than G prime. What if it is trivial? So if it is non-trivial, you're done. You are assuming U is in the B prime. Then do you agree that B prime is non-trivial? Then you are done. The only issue is what if B prime is exactly the vertex U? Then you should Okay, so I'll give a hint. Anybody else? Okay. Okay, so I'll give some hints. The easiest case in a certain sense is the last case. This will be our 2.1. If U is a vertex of an even component, see if you can figure that out. The thing you have to pay attention to, what is the difference between G prime and G? The only difference is these capital F edges. They are all incident at U. Right? So, if U is in an even component, it turns out you can show quite easily that there is a non-trivial barrier in G. That's one case. If U is in the barrier itself, if the barrier is non-trivial, you're actually done. You all agree? If U is in the barrier and the barrier is non-trivial, then you're done. The same set is a barrier in G. Non-trivial. The problem is if it is a trivial barrier, if it contains only the vertex U, well then you have just shown a trivial barrier in G, that doesn't help at all. So then you have to do some work. Maybe you can throw some vertex in it. If you can throw some vertex in it and show that this is still a barrier, then you are done. And then comes the last case, which is the hardest case. Even in this case actually, if the barrier is non-trivial, then you should be done, no? Use a vertex of an odd component of G prime minus B prime. All the edges in F are incident at U. Okay, we have to argue. We will show that this case also can be done. The problem is if the barrier is trivial again here. That will be actually the hardest case. We will show two suppressions. Right? So let's proceed in this order. Let's proceed with 2.1. Yeah. So U belongs to, U is the vertex of an even component of G prime minus B prime. Let's just make a drawing. So I have a barrier B prime. Of course it is trivial or non-trivial, I don't know. This could be trivial also. I have some odd components. Well, as many as the number of vertices and have some even components. Could be as many. U is a vertex in one of the even components. This is in the graph G prime. In some sense, you should forget this drawing. Well, you can keep it in mind, but you should also make a drawing which doesn't have the unnecessary information. Right? So look at this drawing. What is the difference between G prime and G? We are just going to throw some edges incident at this vertex. Right? All the edges in G that are not in G prime, they are incident at the vertex U. You all agree? Right? So the problem is, when I delete this set in G, in some sense all of these will still be odd components. The only problem is those edges of capital F could go like this. And now because I am not deleting U, but I am deleting these vertices, these could become a single component. Right? If the capital F edges go like this. But we can do something. What can we do? We can throw away U. We can include U in the barrier. Now these will all be odd components. So we will still get K odd components, but we are deleting K plus 1 vertices. Therefore, there will be a K plus 1 odd component somewhere. Yeah. So observe that in this case, I don't care about all this. And in fact, there is another good thing that happens when you add a vertex. Now your set is non-trivial. Even if it was originally trivial, it was definitely not empty. Talmadge-Mendelssohn barrier is not empty. Even if it was trivial, now it is non-trivial because I added a vertex. Observe that B prime plus U is a non-trivial barrier in G done by star. Yes.
Is it particular location we are taking B prime to be in? Like, is it in X minus U or?
Doesn't matter in this case. In this case, it doesn't matter. Yeah. So the point is, you could of course consider cases based on where is the action. Is the action on the left side or the right side? But at least in this case, that is just noise. So we will not even worry about where the action is happening. Yeah. There might be another way of doing the case analysis that considers that. Right? So that is what Srijit was also trying. Supposing all the action is happening on the left side, all the action is happening on the right side. Let's actually relate this to that. Now we are going to be in the case where 2.1 does not hold. Right? 2.1 is already done. So now we have to deal with 2.2 and 2.3. Either U is in the barrier or U is a vertex of one of the odd components of G minus B prime. In both of these cases, I claim that the action is happening on one side. If U is in the barrier or U is a vertex of one of the odd components of G prime minus B prime, then I claim that all of the action is happening on the right side because of the conclusion of lemma 5.5. Yeah, so let's also note that. Now suppose that 2.1 does not hold. This means that the barrier itself and vertex sets of all odd components of G prime minus B prime, they are all subsets of the right hand side. X bar plus U. You all agree? Right? Either the vertex U itself belongs to the barrier, in which case the barrier has to be on the right side and then everything has to be on the right side, or the vertex belongs to odd component, vertex U belongs to an odd component, in which case that odd component has to be on the right side, but then everything has to be on the right side. Yeah? Okay. In this case, let us make a observation about, in this not 2.1 case, the graph induced by X minus U is a connected graph. Therefore, it has to be completely contained in some even component. Yeah, you all agree? Because all the action is happening on the right side. The left side has to be a subgraph of some even component. Let L denote the even component of G prime minus B prime such that the graph G prime induced by X minus U is a subgraph of L. Do you all agree? Is this okay? There is an even component of G prime minus B prime, and the entire left hand side is a subgraph of that even component. Yeah? Because it's a connected graph and the B prime is entirely on the right side. Yeah? Okay, this will help us in cases 2.2 and 2.3. So now let's proceed to 2.2. The vertex U belongs to B prime. Let's make a drawing of this situation. So maybe I'll draw it here. This is B prime. This is the vertex U. There are some odd components, 5, 5, and a bunch of even components. This is all happening in the graph G prime. One of these even components is the component L, and all of the X minus U stuff is here. Yeah. Now the only edges we are including when we go from G prime to G are all incident at U. Well, that's good news, right? We are deleting B prime anyways. So we will also delete those edges in capital F. Yeah? Do you all agree that G minus B prime is equal to G prime minus B prime? All the edges are gone anyways. Observe that G minus B is exactly equal to, G minus B prime is exactly equal to G prime minus B prime. Everybody agrees with this statement? Yeah? Those edges don't matter. They're deleted. So therefore, if this were non-trivial, we would be done.
Yeah.
The only issue is, it could be trivial. Well, if it is trivial, let's make it non-trivial. Right? How do we make it non-trivial? Add one vertex from somewhere. From where? L. L was defined for a reason. Take a vertex from L because L exists. L is not empty. L exists. Right? Take any vertex from L, throw it into B prime. These are still odd components. Therefore, there is another odd component. fact, you can see that the even component will actually give you at least one, therefore exactly one odd component. Right. Once you get a non-trivial barrier, there's nothing to be done. So in fact, we don't even need to worry about trivial and non-trivial. Because L exists, I can just throw in a vertex and make a non-trivial barrier. So why do I even need to have two cases? We'll have only one case. Right? Let W be any vertex of L. Observe that B prime plus W is a non-trivial barrier of G, and we are done as always, but not always, by star.
When
Yeah.
you remove a vertex from L, need not be connected also, right? Because L is connected.
L is, yes.
Removing a vertex may have more components.
That's right.
Can we have more node components?
No, we know the original graph is matching code, right?
Yeah.
So, yeah.
Yeah.
So you will get, in fact,
Exactly.
yeah, you will get exactly, one odd component. Yeah. So in fact, it proves multiple things, right? If you can create a situation, so actually I have an exercise for all of you, which I did not do myself. Create situations, create concrete examples where all these cases arise. We will do one case at the end, but for all the other cases, see if you can create concrete examples of matching code graphs and non-trivial tight cuts where these situations actually arise, right? And if you can't create concrete examples, come up with a more fundamental contradiction to some cases. Right. Yeah. But yeah, the point is, in fact, if this works, then it means that this is a two connected graph. You delete one vertex, you will get one odd component, and these components actually don't exist. There's a single even component. Right. All these things follow. Yeah. Right. Okay, so we are done here also. Everybody agrees? All good? So we are now left with 2.3. So U is vertex of an odd component. Let me call this component K of G prime minus B prime. Yeah, this is a case that remains. Let's make a drawing of this situation. So we have a barrier. We have as many odd components. And we have possibly some even components. There's a particular odd component that contains the vertex U. I don't know how big it is. I just want to highlight it. All the edges that we are adding to go from G prime to G, they are all incident at this fellow. Right? Oh, do we know the other end of those edges? Huh?
Yeah, in some even component.
Which even component?
L.
L. Let's go to this drawing. It was drawn for a reason. All these edges are going into x minus u. X minus u is a subgraph of the L we defined somewhere. So all the edges that we are throwing back to go to the graph G, they are actually going from U into a particular even component called L. Okay, so let me highlight L. This is my component L, and all the edges, maybe I'll put this here on this side. All the edges will actually go here. And maybe I'll put some edges, why not? Let me put some edges. How many did I have? I had 3 edges there. I'll put 3 edges. All these capital F edges, these are the capital F edges. If we include them, we are in the graph G. Yeah? This is the difference between G prime and G. So in what cases are we done?
If B dash is not trivial.
If B dash is non-trivial, we are done. If B prime is non-trivial, we are done. You all agree? Yeah? Because these fellows are still odd components. I have k vertices, I have k minus 1 odd components, I am done. Right? These edges do not affect these odd components. Their edge is still going to be prime only. Right? These edges are not going to be incident here. They are incident like this. So if B prime is non-trivial, we are done. You all agree? Convince yourself that the drawing is not fooling you. Right? The drawing has all of the information we need. Right? The main point is each edge of F, each edge in F has one end in the vertex set of K and other end in the vertex set of L. Therefore, if B prime is non-trivial, then B prime is a non-trivial barrier of G, and we are done by star. So the only case that remains now is that B prime is actually trivial. There's only one vertex in B prime. Yeah? Everybody agrees? Okay, let's redraw to reflect that. So this is not what it looks like. It's just a single vertex. This is our barrier, and therefore all of this disappears. Right? Number of odd components is equal. So there's only one odd component, K, and there is an even component for sure. L exists, right? Everybody agrees? Yeah? That did not change anywhere. I claim that we are again done. And DIY, and I'll come and talk to you. DIY, finish the proof from here. What is your vertex here? Right. There is only one thing that is missing. There is one small detail. My question to you is, somewhere you should use some factor. And not in case one. Because if you are never using not case one, then why will you do case one?
reducible and everything, but how exactly is case 1 useful here?
No, case 1 is not useful. Not case 1 is useful.
Yeah, that's what I mean. Oh, okay. Yeah, please.
Are on the right side. So therefore, even after you leave the barrier, this is still connected somehow. So it is connected in one even concept. That is already defined. How to do it? Right. Good, right? Yeah, that's one of the things I have in mind. See if you can eliminate case 1, optimize the proof. So this is already very optimized. But who knows? Maybe there's more optimization.
So that is, I think I'll be no, this is
These are just connected somehow. So you have to show me at least one outcome. Two vertices.
then why it should be disconnected and that we have.
Yes, it should be just.
Starting point.
So that there's only one issue. You should use somewhere the entire proof. Somewhere you should use not case 1. And like that. So that is the small details. Even one
Other than that, then just put the word on there.
Sure. Yeah.
But if there is no or
Even highways is only at K.
yeah, then
Right. It is. My concern is floating leaves is a trivial component. It can't be, but you have to prove it.
Is it the case that U has neighbors in X other than, so V has neighbors in X other than U?
V has neighbors in V, I don't know where it is.
So U V differentiation.
Yeah, but I don't know where V is in this picture.
I don't know, I'm just asking about that.
Ah. So we know that U definitely has some neighbor on the other side. That's R. Whether V has neighbors in X that are not U, we don't know. Because case 1 said that neither of them has any other neighbor on the other side. In case 2, we just know that one of them definitely does. And without loss of generality, we put it to be U. But this is the right way.
so this
Right. Yes. Right. But in this picture, whether you as a neighbor is X bar. So that neighbor has to be where it is. So one is here, yeah, and other could be here. Can it be here? Can it be here? Remember, these are components treating this right. They are components of treating the vertex. So it can't be there. So where is it? It has to be here. That is actually important. This is the important part of Okay, anyone else? Right, so the point is that since bicritical graph exists, since they exist, you can't always conclude that the graph is not bicritical and finish the proof. Somewhere you have to deal with the case that the graph could actually be bicritical. Right? Otherwise, your proof is not correct. So, if the graph is bicritical, then the ELP theorem basically says that there must be a two separation cut. There can't be a non-trivial barrier cut. So therefore there must be a two separation cut. So somewhere in the proof, we should find a two separation cut. We can't always find a non-trivial barrier cut, right? That seems to prove a much stronger statement, which is false. So somewhere in the proof, we need to find a two separation cut. And this is that point in life. Right? So here I claim that there is a two separation. Right? And the candidate is quite natural. You all can probably guess what the two separation is, right? Okay, what is it?
U union B dash.
U and B dash, right? There's only one vertex here, and this is the vertex U. And you would like to argue that these two vertices comprise a two separation. That needs to be argued. So the claim is that B dash B prime plus U is a two separation in G. If we prove that it is a two separation, we are done. Two separation always gives rise to two separation cut by definition, right? So everybody remembers definition of two separation. It's a two vertex cut that is not a barrier. That's the definition. In other words, you get only even components. So if you delete this vertex, let me give it a name for now, I don't know, Z. If I delete U and Z, what is clear is that this fellow, all its neighbors in G are either here or here. Yeah? In G prime, all the edges from L were going into Z. These are the capital F edges. They go between L and the vertex U. Therefore, if you delete U and Z, this is definitely a component. The problem is, this could be the only component, in which case you haven't proved anything. Right? You need to show that there is one more component. K minus 1 doesn't work here. You delete two vertices, you tell me you got one component, that doesn't imply there is another component. It would if the component were odd, but the component is even. Therefore, it doesn't imply that there is another component. The whole graph could be L, Z and U. This could be the whole set of vertices. That will happen if there are no other even components. So let me erase them. Because if there are other even components, then anyways we are done. Multiple ways to finish the proof. This is the interesting case. Forget the other even components. Right? They may or may not exist. In this case also we need to prove that there is yet another even component apart from L. Where will that come from? It has to come from here. There is nothing else in my drawing. Right? So if we show that this is non-trivial component, then we are done, no? So we have to argue that this is non-trivial. We never argued that. Right? Just because my drawing looks like this, it doesn't mean it is non-trivial. Right? So we need to argue that K is indeed non-trivial. But K is non-trivial. Why? K is non-trivial. If we argue that K is non-trivial, we are done. So, to prove this claim, it suffices to argue that the vertex set of K has at least 3 vertices. Convince yourself of this. If we argue this, we are done. Then this is definitely a 2 separation. We got one even component and we will get another even component here. In fact, if you get one even component and you get one more component, that has to be even. Because otherwise the 2 vertex cut will be a barrier and then you can't have any even components, right? So all you need to argue is that this is non-trivial. Right? If it is trivial, then well, you haven't proved anything. Right? Okay. So go ahead.
So we use the fact that U has more neighbors and
Right. So U, this is a component. If you can show that U has some neighbor here, then you will be done. Right? And that is what I'm really saying. U has some neighbor in X bar that is not equal to V. We assume that we are not in case 1, and therefore we adjusted notation so that U is the fellow who has a neighbor in X bar that is not equal to V. Where is that fellow? Let us give it a name. W. Can it be in L? No, it can't be in L. Because if it was in L, then you would have a non-yellow edge going from U to that vertex. But non-yellow edges don't exist going from here to there. Right? Right? So therefore, that fellow W, well, it is not, can it be equal to Z?
Then V.
Can it be equal to Z? Oh, but then V.
V.
Ah.
Then V is our choice.
Then we choose V, right? So therefore, there is a neighbor of U that is not this fellow and that lies in X bar, because U has, maybe I should not give it a name. The point is U has at least 2 neighbors in X bar. Those neighbors cannot be here. Those neighbors could be Z or here. So there is at least one that is not equal to Z. Therefore it lies here. Therefore this is non-trivial. Therefore we approved this statement. Therefore we approved this statement. We are done. We got a 2 suppression cut.
One more vertex will be there.
Sorry? Oh yes, there will be more. There will be more. Yeah, that's right. Yeah, that's right. Because it is odd component, if I show 2, it has at least 3. You're done. Yeah.
No. And hypomatchability also used here because it has to be connected. Those 2 vertices.
I don't even need hypomatchability. I know it is an odd component. I know it is a component with an odd number of vertices. So we are just done, right? If we just show that it is not singleton, we are done. Right? So we don't need
After
to use.
removal of U, that's
Yeah. So we just need to show that it is not equal to 1. Yeah, actually that is probably better. Yeah, that is probably better. This is all we need to do. Yeah. So somewhere in the proof we should find a 2 suppression cut, right? Otherwise we are proving that every time there is a non-trivial tight cut, there is a barrier cut. That's not true. Yeah. So this finishes the proof of the ELP theorem. This is a very, very optimized proof. I agree that it is, so it seems a bit magical if you are not the one who proved it. But that is most of mathematics. Pretty much any non-trivial result, if you did not prove it, for a long time in your life you may feel it is magical. Right? It just is a matter of time. So of course, they did not come up with this overnight. Right? The theorem was proved in 1982. This is a proof from 2018, which was possibly simplified further before the book was published. So in a span of 40 plus years, by people who spent several decades in the area. so I think this idea of Dulmich-Mendelssohn barriers actually came up in the CLM 18 paper, and since that paper and that process, they became big fans of Dulmich-Mendelssohn barriers, and they realized that they are actually very useful, right? And it is naturally tied to the Dulmich-Mendelssohn decomposition of bipartite matchable graphs, which is why they call them Dulmich-Mendelssohn barriers, right? So this Dulmich-Mendelssohn barriers turned out to be very crucial, and this lemma 5.5 is really essential to this entire proof, right? The existence of special types of Dulmich-Mendelssohn barriers is what makes everything work in this proof, right? And yeah, I do have some questions which I'm planning to send to Claudio, but before I send to Claudio, maybe you all can think about it. So So the ELP theorem says that there is always an ELP cut whenever there is a non-trivial tight cut. And we also discussed in an earlier lecture, but we will not be proving this theorem in this course, the laminar ELP theorem, which says that for any given non-trivial tight cut, there is an ELP cut such that these two are laminar. That's much stronger. Right? But that proof is much harder. There's a reason they did not include it in the book, which is also why we are not going to include it in the course. Right? There's only so much time. But here is another statement I have. Is it true that every matching covered graph that has a non-trivial tight cut has a peripheral cut that is an ELP cut? We know that an arbitrary peripheral cut need not be an ELP cut. The standard example that we have, right? Let's draw this example. Is actually related to the next DIY. So let's draw this example. This is a peripheral cut, peripheral tight cut that is not an ELP cut, right? Therefore, you should be able to run the proof on this example, right? This proof, by the way, if I am not mistaken, this proof can be converted into a polytime algorithm. What is the input? You give me a matching code graph, you give me a non-trivial tight cut, and I need to return to you an ELP cut, right? And I think that this proof, you can just convert everything in this proof into a polytime algorithm. I have not verified it. See if you can work out the details, and if you get stuck somewhere, then let me know, right? So that's a DIY. Well, it's a DIY. I'm not going to discuss it. Convert this proof into a p-time algorithm, right? So the input is a matching code graph. You are given a non-trivial tight cut, and the output should be an ELP cut. If the original tight cut given to you is ELP cut, nothing to do. Otherwise, assume it is not an ELP cut. But maybe in the proof you need to take. You are given a tight cut with the property of peripheral cuts. This edge such that the graph induced by x minus u and x bar minus u are both connected, because we are starting the proof through such a cut. So assume that you are given a cut like this, which has this property, right? And now return an ELP cut by running this proof. Yeah.
But we can do that directly without.
Oh yeah. There are other. Yeah. I want to deliberately think about this proof. Can this proof be converted into a polytime algorithm? But yes, in general, because of the ELP theorem, you can always find a non-trivial tight cut in polytime, because you either find a barrier cut or a two-separation cut, and that is much easier. So that is definitely, that supersedes this exercise. This exercise is more just to get a deeper understanding of the proof itself. Can you do all the steps of this proof in polytime, given a tight cut with that property? Right? So that's one point. So run this and another, here's another DIY. Run the proof on this example. Where the cut given to you is this cut C. This is the original cut given to you, which we know is not ELP. But it has that nice property because it is a peripheral cut. By lemma 5.1, it has the property. Yeah? Okay. So my question is it true that every matching covered graph that has a non-trivial tight cut has a peripheral tight cut that is an ELP cut? I don't know. I'm sure Claudio has some thoughts on this. Maybe as a counterexample. Right. So this is one question. You can think about it. Here's another one. This is motivated by the laminar ELP theorem. Given a non-trivial tight cut, is it true that there is a tight cut that is laminar with this one, and it is a peripheral ELP cut? I don't know. Just curious. Right? Maybe there are easy counterexamples. I haven't thought about it. Right? If I do all the thinking, what will you do? So you think. I thought enough to present this. Okay, good. There was a question there. Yeah.
Can you repeat the earlier question?
The earlier one was basically, let's just So my earlier one was there exists a peripheral ELP cut. There exists a peripheral tight cut that is an ELP cut. In any matching code graph that has a non-trivial tight cut. And the second one says that given any non-trivial tight cut, there is one that is peripheral ELP cut and is laminar to the original tight cut. For any non-trivial tight cut C, there exists a peripheral tight cut D that is an ELP cut such that C and D are laminar. Of course, and the other question is, even if you prove all these results, what is the application of it, right? Can you actually use it to prove something else interesting? Some nice corollaries. I don't know. Right? Okay, so I think that's all for today, at least from my side. Questions, concerns? We can wait for a bit, see if there are any other questions or concerns. It's given too much information to everyone.
How that one is not a barrier? Z and U is not a barrier.
Z and U.
Is not a barrier.
Well, it can't be a barrier, right? Because you are getting an even component. If you are getting an even component, anyways, it can't be a barrier. Barrier should not give you any even components. Right? So that is one way to justify it. But in fact, what will happen is when you delete Z and U, you will get one even component and you may get multiple even components from here. You can't get any odd components from here. That would be a contradiction to the fact that this is a matching code graph and you are getting a barrier with an odd component. Well, barrier with an even component. That's a contradiction. So therefore, all such examples, ZU will not be a barrier. Okay, good. Any questions, concerns? Everybody's okay with the proof? Yeah? So I strongly suggest going through this proof again. See if you can reconstruct all the arguments yourself, right? And get a deeper appreciation of it. Right? Seeing it one time definitely is not enough. I saw it one time during my postdoc years and now I know that I did not absorb much. I mean, I struggled through it, but now I think I have a much better understanding. Yeah. Alright, so you may stop recording and we resume next week. So I think no more lectures this week. We will have our next lecture. There's one more thing. Yeah, we can stop the recording and then I'll discuss the logistics. Thank you.